What I'm going to do now is introduce you to our first panelist. Dr. Andrew Bengsen is from New South Wales DPI, talking to us today about the practicalities of camera trapping to detect and count pigs. Andrew's got over 15 years experience in pest animal management and research and has been with the Vertebrate Pest Research Unit since 2011. I'll let Andrew talk more about his expertise within his presentation, but I just wanted to say thanks, Andrew, for your time and commitment today. And again, just a reminder, any questions that come up on the fly, please put them in the chat function, and we'll have plenty of time later if Andrew doesn't talk for too long in the question and answer session to address those. I'll leave it to you, Andrew. Thanks again.
Great, thanks, Ricky. I'll just power through this reasonably quickly. All right, hopefully that screen has come up now. So I'm going to be talking basic sort of level about some of the practicalities of using camera traps to detect changes in feral pig populations over time. Just a caveat to start with, I'm not an electrical engineer or a camera technician or anything like that. I'm a wildlife ecologist. I started using camera traps to monitor changes in pig activity in response to management back in about 2006. And I've been doing it with pigs and other species ever since. So what I'm going to talk about today is based on things that I've learned from practical experience and things that I've learned from other people's practical experience, from colleagues and so on as well. So it's all sort of pretty practical based, I think. So I guess this talk has kind of got three main sections. So we're going to talk first of all about using or selecting the right tool for the job, how to set up cameras to detect pigs, and how to go from a bunch of photos from cameras to data to inference about a pig population. And some of this stuff, as I said before, it's pretty basic level. Hopefully I'm not telling you all to suck eggs and not telling you things you already know, but we'll see as we go along. So the first thing I think we need to talk about is what kind of camera is best fit for purpose. And I use the word, fit for purpose here, rather than best camera overall, because the type of camera that we choose is really determined by, or the best camera for our purposes is really determined by what we're actually trying to find out. So the first thing we need to do is be very clear about what it is we're actually trying to find out or estimate about the population, and that will guide our choice of hardware. So there's a lot of different cameras out there. They've got various different functions. A lot of them are trade-offs in cost, memory capacity, sensitivity of the sensor, battery life. But we need to think about what kind of, I'm not going to go through all these in detail because we're here all day, but we need to think about what kind of triggering we want on the camera, what kind of flash we're going to want on the camera. That'll depend on what we're trying to figure out. What kind of sensor, how sensitive it is, the dimensions of the detection zone. I'll talk a bit more about that in a minute. Need to think about the image quality, whether we want low quality and lots of images or higher quality and fewer images. Where the images will be stored, whether it's on the camera or at a sort of a local base station, or whether they get sent back over the network, back to phones or things like that. And the programming flexibility of the camera. So some cameras have a lot more flexibility to alter some of these traits, others they're quite fixed. And of course, it all comes down to a bit of a trade-off in costs as well. So I'm just going to spend a bit of time talking about detection zones. So all the different cameras, they all have slightly different detection zone characteristics. Now, it's a common trap to think that, you look at the image, the photo that's taken on the camera, and you think that any animal that might move in front of there and appear in that image is going to trigger the camera, but that's often not the case. So these Reconyx cameras you can see on this slide here, they're quite popular for good reason. They're pretty reliable. They've got a good detection zone. And this graphic here just shows that the zone at which the infrared sensor operates matches quite well the field of view of the camera itself. So you've got a 40-degree angle out from the camera, that the sensor is operating over. So animals that move in that area are at risk of triggering the sensor, and that corresponds pretty well to the actual field of view. But not all cameras are like that. So when I first started out, 15, 16 years ago, whatever it is, I was using these old cameras that had a very narrow detection zone, much like the one in this image here. So here we can see it's only 14 degrees wide, much narrower than the actual field of view that's going to show up in the camera image itself. And it only goes about 36 feet out from the camera. So an animal would have to be moving around in this space here in order for it to trigger the camera. And as I said before, most cameras have got slightly different detection zones. So it's really important to understand how your camera operates and how its detection zone operates. So going back to the Reconyx, which is the wider detection zone on the left, just to give you a bit more information about it, this illustration here shows a photo taken from a camera, and superimposed over that are the detection zones on that camera. So in order for an animal to trigger the camera and take a photo, what it needs to do is it needs to recur inside one of these two parallel red bands here. And it needs to move from one of these vertical zones into the next one. So this deer here that's moving from zone 6 to 5 inside this red area will trigger the camera. Similarly, this one moving from 5 to 4 inside a red zone here will trigger the camera. This deer up here in zone 1 on the left-hand side, outside the red zone, it's in one detection band. It could move around backwards and forwards and up and down here all day and never trigger the camera. So it's just important when you're setting up the cameras to understand how that works. So some colleagues of ours at New South Wales DPI did a fair bit of work, pretty exhaustive work a few years back, looking at how best to orientate cameras on trails and tracks to maximise the probability of detecting animals moving down those tracks. And what they found was that, at least with the Reconyx cameras, it was best to have them at an oblique angle, around 20 odd degrees, to the track, and that maximised both the probability of the sensor going off and also the probability of the animal still being in the frame of view when the sensor goes off and takes a photograph. So this, based on that and based on some work that I've done previously, I've sort of mashed them together, and this is our sort of standard method here for setting up a camera trap to detect pigs or other sort of largish bodied animals like deer and that sort of thing. So what we do is we'll set up a post, just a small garden stake or a little tomato cane or something like that, about 6 meters out to the front of the camera. And we figure anything from that post to the camera, we've got a very high probability of detecting. We'll set up the camera on that oblique angle to the game trail, again, to maximize detection probability. And we try and standardize that as much as possible across all our cameras in a grid. Now, for camera height, you know, you tend to get the best detectability if you've got your camera parallel to the ground. So we'll set it up so that the camera is parallel to the ground and aimed at a height of about 50 centimeters at that 6 meter mark. So in this little graphic here, we've got a camera here in blue. Here's our 6 meter stake out here. Here's our game trail in yellow. So we'll put the stake just outside that target zone here. And the grey triangle here represents our detection zone. So anything moving up and down this trail here is almost certain to trigger our camera. Now, if we're operating on something that's less than a perfect pool table for terrain, again, it's the 50 centimeters at our 6 meter mark that we worry about to maximize that detection zone, to maximize our probability of detecting anything moving in our sort of target area, which means our camera will have to move up the tree a bit higher. So people often ask, you know, what height should you set the camera up the tree? Well, don't worry about that. Think about how high out you want the beam to be going in your detection area. And this is just an example of a setup here. This is for deer down in Victoria. But the same principles apply. We've got our camera here in white, we've got our 6 meter post here. Here's our game trail. And this field officer here is just moving down the trail, testing that the camera is actually going to work as we expect it to. And that's always worth doing as well. Make sure you use the walk test function or have a walk past it and check your images and make sure that it's performing in the way that you expect it to before you leave it there. Just one other thing I'd like to say about the mechanics of cameras is that they operate on thermal contrast, at least these passive infrared ones do. So they work, they'll be triggered if it's not just by an animal moving in front of the camera, it's not just moving itself, it's the contrast of that moving body against the background. So if you've got a warm pig moving in front of a relatively cooler background, chances are you'll get a photo. Similarly, if you've got a cool animal moving in front of a warm background, you'll get a photo. If you've got a pig covered in mud or water emerging from a water hole, and it's the surface of the pig is much the same temperature as the surface of the background, chances are it's not going to take a photo. So you just need to think about that when you set up your cameras so that you're optimizing that thermal contrast. And finally, on that side of things, a couple of good manuals, a couple of good reference manuals if you're into some of the practicalities. Want to find out more about this sort of stuff. These are pretty good. They're getting a bit on now in some of the details, particularly about analysis and stuff, but the backgrounds of how cameras work and how to set them up, there's some good info on these guides. Okay, I'll just go quickly now about some of the things that we can use cameras for. So, I started off looking at feral pig behaviour around control operations. So, cameras are great to stick on bait stations if they're not going to disturb the pigs. So you can understand how many animals are moving into the area, how much bait you're going to need, when to swap out free feeding for poison bait, that sort of thing. When your number of pigs visiting plateaus, for example. Understand if pigs are actually eating the bait, if they're just coming to visit and moving on, if it's not attractive to them. You can have a look at how pigs are interacting with other control tools like traps. Why all your traps are being set up all the time, but you're not catching any pigs, for example. And also, you can look at some issues around impacts, like damage caused by feral pigs as a result of their behaviour. But that's enough about that. We'll get into the population side of things. I'm going to talk about 3 different sort of levels of complexity for understanding what's going on with pig populations based on camera trap data. So the first and simplest sort of thing that we can do is a relative abundance index. So understanding whether or not the activity, I should really call it relative activity index, but whether or not feral pig activity changes over time and how it changes, if it's going up or down, and how much it changes by. So here we have an example. This is some work that Darren Marshall has been doing up in northern New South Wales. I've been working with him and his team to help them out with that. So they've set out quite a big camera grid here, 101 cameras. We've got good results on this view as 20 cameras, but it really depends on the site and the pig population. There's a good grid here, 101 cameras spread over an area, about 800 metres apart, these cameras. So the type of data that we need for this basic, simple level of understanding is just repeated detections of pigs over days or weeks at different cameras. The complexity, pretty simple. The type of model that we need to get some info out of this data is pretty simple. Basically, we're estimating the expected number of pigs detected per camera per day and how that changes over time. And we're estimating, importantly, we're estimating the precision or the uncertainty around that index as well. Without that uncertainty estimate, you've just got a number, you might as well just have a random number generator. An index is meaningless without an estimate of uncertainty. The output of this type of model is, it's a combination of both the detectability, so the probability of detecting pigs that are present and available to be detected, and the number of pigs. And we can't really separate that detectability out from the abundance. So that imposes some limitations on the kind of inference and understanding that we can make from this model, but it doesn't mean it's useless, far from it. As I said, well, I guess what it really means is that it's most useful when you're looking at a situation where you expect the change in pig abundance to be much larger than the change in detectability. So for example, when you're comparing a couple of indices that are index values that are close together in time, separated by a major population control event. And we'll look at an example in a minute. In that case, you'd expect large number of pigs removed. The number of pigs removed is going to outweigh any small change in detectability. So we can use it to see if the population is going up or going down over time. The limitations is, like I said, it's confounded. We don't really know. We can't be 100% sure whether changes are due to abundance or detectability. And also it's kind of vague. It doesn't tell us anything about the actual number of pigs in the area, but it does tell us the direction of change. So these are the camera stations. This just shows over 3 months, just the sum of pig detections at each camera's, larger dots, more pigs. So we broke this data down. We had a year's worth of data. We've got a bit more actually, but I'm not going to show that here. We've got 4 months here prior to any control going on. You can see there's a bit of variation in the first couple of months. I'd suggest that decline between January and February is probably due more to detectability than to abundance, probably as a result of pigs changing their activity in the heat, but hard to tell. We then have a control operation, an aerial shooting operation in late April 2020, and a substantial decrease of about 41% in pig activity following that aerial shoot, and pig activity stayed low throughout the remainder of the year. And when we looked at the stats, it was the type of model that we used allowed us to conclude that there was a 99% probability that this is a real and genuine decline in pig activity, given the data and the model that we had. Now, because that index is confounded, again, we can't separate that detection probability from the actual numbers of pigs. A lot of people like to use occupancy, which does explicitly separate detection probability and population status, but it doesn't tell us, again, anything about the number of pigs. So occupancy allows us to estimate the proportion of area that's used by pigs. And it relies again on repeated observations of pigs at cameras, but these cameras need to be far enough apart that the detections are spatially independent. So we're not getting pigs detected on one camera or more than one camera during the same survey period. So the cameras have to be a fair bit apart. It's more complex to use than the basic index. It's relatively easy to plug in numbers and get numbers out, but if you actually want to make some reliable inference, it can get pretty complicated. Not overly so. The output, as I said, it gives you an estimate of the proportion of the area that is actually occupied by pigs, whether or not pigs are actually detected at each site, which can be of interest in itself. It's good for looking at the distribution of pigs and how that changes over time. But its big limitation is that it doesn't tell us anything about the change in the numbers of pigs. So if you imagine, say, a site where you've got pigs occurring in groups of 10, so there's 20 groups of 10 pigs spread throughout a site. You go through with a helicopter, you shoot 9 pigs out of every 10. Massive change in abundance, 0 change in occupancy. As long as you've still got 1 pig in that group, that site is still occupied. So it doesn't really tell us a lot about abundance necessarily. And finally, if you're in the happy position of having a lot of pigs that you're able to recognise, either from individual natural markings or even better by telemetry, by GPS collars like this, then we can start looking at some really useful information and start estimating the actual number of pigs in the area, the actual density, number of pigs per square kilometre or whatever. And this is something I've been doing a bit of recently, in recent years with deer. We've got a paper coming out soon, hopefully, on that. And we've just started doing it with pigs as well, and it's working really well. Again, working with Darren Marsh and some of his collared pigs. So if we can recognise individual pigs, and we can reliably locate them in space and time, and we're getting pigs detected at different cameras, then we can start to use these models that will allow us to estimate actual density of pigs. I'm not going to go into detail about this because it's quite complicated. Just let you know that it's out there and it's a possibility. So this is an example from that site that I showed you before. We've got a bunch of collared pigs here. We can see exactly where and when they show up on the cameras. And we can estimate other functions relating to their movement from the telemetry data, although we don't need that. We can do it if we can just recognise pigs from their coat patterns, for example. And this allows us to estimate the actual number of pigs there. So the data type that we need is spatially correlated detection. So we need detections of individual pigs at multiple cameras. So the cameras need to be reasonably close together. We can also add other sorts of data in there. It's quite a flexible modelling system. The more data we have, the better information we get. So like I said, we can, if we have it, incorporate telemetry data, for example. The complexity here is horrendous. I've been working on this for a few years now. I think I've got a pretty good handle on it. but it's not something you're going to just sort of do off the back of the envelope. The output is, yeah, as I said, it's density or abundance, the actual number of pigs that are in an area. Its great value is in understanding, for example, how much of a difference did your population control program make? You know, what proportion of the population did you actually remove? Not just did you kill enough pigs to notice, or even predicting how much control or how much of a difference you need to make if you want to, say, suppress population growth. You know how many pigs you've got to start with. You can work out how many pigs you've got to remove in order to stop the population growing year on year. Big limitation here is pretty labour intensive, going through the camera images and that sort of thing, although Chris is going to talk soon about automating that sort of process. But still, the modelling itself is quite labour intensive, and it requires a fair bit of know-how. And also, because the cameras have got to be reasonably close together, it puts a limitation on the site size. So in our case, probably a distance of 800 metres to 1,000 metres seems likely to work pretty well in most cases. So to wrap up, I would just say, you know, there's a very broad sort of overview of a bunch of different things there, but the main take homes I'd like to leave you with are that if you're going to start using camera traps to monitor pig populations, you need to set meaningful aims up front. Know what you're trying to do and why you're trying to do it. Get to know your equipment, play around with your cameras before you put them out, try them in different situations, read the manual, understand how they work, understand the limitations. Same with your analysis method, understand its limitations or understand your analyst's limitations and potential as well. And importantly, you need to start with the outcomes that you're after. Let the outcomes determine the methods that you use, and the methods that you use will determine the gear that you require. So often you see it the other way around, but yeah, always outcome to methods to gear. So that's all I've got for now. Happy to take any questions later on when we get around to question time, or in chat or anything like that. And I'll save a copy of this presentation at that website down there as well. Thanks.
Thanks very much, Andrew. Really good to hear some of the, as you mentioned in your topic, the practicalities. Sometimes we don't focus as much on the practicalities, and that's what kind of depicts if your cameras work or not, if you get good data. Yeah, thanks again. Some really good information, a lot of information there we've gone through.